So, you didn't have to record me as well, Right. Well, welcome to our Zoom night. Tonight we've got a bit of a difference. We're going to have a little bit of a talk from Nick M0NTV, and he's going to give us a talk on 40 meters on a glue stick. Now, I've been trying it all afternoon. I've had a glue stick stuck in my ear and everything, and I can't hear 40 meters on it, so I don't know what he's going to do, but yeah.
Propagation. Oh, good today, see.
Yeah, well, let's have a look at it, and then we can see it. Now, it would be best if everybody muted themselves except for Nick, and I'm sure he'll answer some questions at the end of it.
Certainly, yeah.
So I'll hand over to Nick or Mr. Secretary there, who knows more about this Zoom thing than I do. I make a complete hash of it, so he'll sort it out, and then Nick, you can give us your nice little talk, if you could, please.
I certainly can. Well, evening all. It's good to be with you again, and I am going to be talking, as you said, about it's a direct conversion receiver. Spoiler alert. But we'll get to the glue stick in due course. Right. So the first thing I'm going to do is share my screen. So hang on a minute. Okay. Unfortunately, yeah. That's all right. Okay, brilliant. So hopefully you can all see that okay. There is a bit of audio and video as well in here. So at some stage you might have to just kind of adjust your volume accordingly. But yes, so my passion really is home brewing in the kind of traditional ham radio tradition, really. So I tend to build things kind of Manhattan style, so little kind of conductive pads glued down to a copper clad board as a ground plane and build them up from that. The thing I do most is really I build transceivers, single sideband transceivers. I think I've just done number 6, I think. But obviously that's a big project and it takes a long time, so interspersed with kind of building the kind of big, huge radio projects, it's good, I think, to really drill back down to the basics, because the truth is, I couldn't ever build any of those big projects if I hadn't, first of all, built some of these smaller ones, because essentially it's the same kind of building blocks that you use for all of these things. As I've probably said before in previous talks, I build in a modular fashion. So that is, you take a project, and instead of trying to build one board and stick it all on and pray that it's going to work at the end, and because it's not, in all likelihood, I break it down into small bite-sized chunks, bit by bit. And when you've built it, then you can test it and tweak it and get that bit working, and then put that aside, then go on and build the next bit and do the same with that. And then you try and get those two bits you've built together to play nicely together, and then you go on to the next bit, and like that. And I found actually you've got far greater chance of success at the end of the day if you can do that, kind of building it and testing it as you go along. So there are, I would contend, essentially only 4 basic building blocks with which you can build any analog sideband radio, which are filters, mixers, oscillators, and amplifiers. Now, of course, these are very wide generic terms. There's lots of different kinds of filters. There's wide band pass filters, there's low pass filters, high pass filters. There's very narrow crystal filters to just let one sideband through. There's lots of different types of mixers and oscillators and many, many different types of amplifiers. But essentially, you could argue they're all just different flavours of these 4 basic types. And the reason why I'm going to build a direct conversion receiver, and why I've built a number of direct conversion receivers, is that it's an interesting design because it's just about the simplest single sideband radio that you can build, because it utilises, when you really kind of pare it down, to just one of each of these 4 different stages. So this is the direct conversion receiver that I'm going to show you how I built. So we start off with our antenna, and I'm going to build this for the 40 meter band. So that goes through our bandpass filter, and then that will filter out everything apart from the 40 meter band, hopefully. And then we pass that signal on to our product detector, which is just a mixer. It's just a mixer that is mixing down to baseband to audio. And a mixer has 3 ports. It has 2 inputs and 1 output. So one of the inputs, of course, is our 40 meter signal coming from the aerial through the bandpass filter. And the other signal is the one we generate ourselves from the local oscillator. And those 2 signals mix. It's not a very good word, really, because they don't really mix in the purest sense. And anybody that's had any dealings with audio stuff, we talk about audio mixers. Well, they really do mix. But actually, it's not really like that with RF. But the 2 will combine and will give you, well, a number of different outputs. But the main 2 outputs that you will get will be the sum and the difference frequencies. We're only going to be interested in the difference frequency, and I'll come on to this more in a minute. And that then will be fed to an audio amplifier and out to our loudspeaker. So it's essentially just 4 modules. Now, I don't know how many people have, well, I'm not going to ask how many people have built a direct conversion receiver, but I'm just going to ask, how many people have listened to sideband on a direct conversion receiver? Because if you haven't, it's a bit of a shock to the system, to be completely honest with you, when you do. Particularly in these days of software-defined radios, where we've kind of got accustomed to these brick wall filters, and of course the thing with a direct conversion receiver, as you can see there, is there really is no filtering other than the bandpass filter, which is letting the whole band through. There's no filtering at all, which means that it can sound a bit of a mess, because there's a lot of different stuff cutting across, and I'm going to explain why that is the case in a moment. Okay, so full disclosure, most of this talk is very practical. I'm going to show you photos and pictures and all the rest of it that I've done. This is the only slide which actually tackles some actual RF theory. To be honest with you, I love this stuff. This is why I build radios in the first place. I do it so I can understand how they work and what's actually going on. But if this doesn't float your boat, that's fine. Just zone out for the next couple of minutes. But for those that are interested in how it actually works, this is how it works. So it starts with a signal coming in through our bandpass filter to our product detector, our mixer. Now, just to keep the maths simple, let's assume that we've got a 3 kilohertz wide signal. Now, in all likelihood, you're not going to have a 3 kilohertz. It's going to be narrower than that, but it just keeps the maths a bit easier. So let's assume we've got a lower sideband signal then that we're trying to tune into, which is lying between 7097 and 7100 kilohertz. So that then is going to be mixed with our local oscillator, and we're going to set the local oscillator at 7100. So what that will do is that will give us, as I said, a number of different outputs from that, but the 2 main ones are what we call the sum frequency. So that is the RF plus the local oscillator. And you can see then, if you do the maths, that would give us a signal lying, well, in the middle of the 20-metre band. We don't need to worry about that because we're going to filter that out. The one we're interested in is the difference. So that's the RF minus the LO. Now, mixers may be clever, but they're not that clever, right? The mixer doesn't know whether it's supposed to be minusing the LO from the RF or the RF from the LO, right? But for our purposes, and me and Bill Maher actually have sold us both. I have a bit of a disagreement about this one, but because he has his way of doing it and he likes to do it. But personally, I think it's much more helpful if you start with the RF. Start with the RF every time, because that will tell you something really, really important about what's going on, which it won't if you start with the LO. So the difference frequency then. So 7100 minus 7100 is 0. Well, you'd expect that, baseband. But hang on a minute. 7097 minus 7100 is minus 3 kilohertz. You think, how can you have a signal at minus 3 kilohertz? Which you can't. Well, you can, mathematically, that's exactly what you get. But in reality, there's no such thing as minus 3 kilohertz. But that minus tells us something really, really important. And that's why I think it's important to start with the RF. So let me show you this, because a picture paints 1,000 words. So, okay, imagine then on the x-axis, we've got frequency. So there's our signal, there's our lower sideband signal lying between 7097 and 7100. Now, what I need you to understand here, that triangle on the y-axis, on the vertical axis, that is not amplitude. Okay, so this might be a bit, this will mess with your head a bit. It's not amplitude. What that is the higher the height of that little green triangle, the higher the frequency of the modulated audio signal. So what I'm saying is what I'm representing here is how that audio, that modulated audio signal is lying within the RF, okay? So you'll see something instantly obvious here, which is it's backwards, right? Because look, if you started at 7100 and tuned down to 7097, the RF frequency, of course, is going down, but the audio frequency is going up. And that's because lower sideband is inverted. That's not going to be a problem because we're going to invert it again and get it the right way round in just a minute. So, but that's how it is. So, okay. So let's say then we're mixing it down to baseband to audio. So what happens mathematically is this, but that can't happen in the real world. So what actually happens is this. Wait for this. 1, 2, 3. It goes whoa, whoa, and it folds around. We say around the DC point, so it inverts, and that's what that minus 3 tells us. It's an inverted form of the signal. But you say, happy days! Look at this, because now we've got an audio signal that is now the right way around, because we've inverted an inverted signal, right? So now it's the right way round. Jobs are gunning, right? What could possibly be wrong with the world? Well, just hang on a minute. Because unfortunately for us, 7097 to 7100 is not the only band of frequencies that will mix down to 0 to 3 kilohertz. If we had, let me show this in yellow. So if we had an upper sideband signal, say, in the 3 kilohertz above our lower sideband signal, because it's an upper sideband, there's no spectral inversion with upper sideband, so it will mix down exactly as it is. So that would mix down too on top of the signal. But I hear you say, who's going to be working upper sideband in the middle of the 40 metre band? Well, probably nobody, but probably what you will have, if it's a weekend, if there's a contest on, if there's a lot of people on the band, is you very well may find somebody is working another lower sideband signal, 3 kilohertz or less, above you. And because that's kind of occupying what would be the upper sideband slot, that gets mixed down as well, exactly as it is, right on top of your signal. So when you listen to SSB on a direct conversion receiver, what you're actually listening to is the signal you want to hear plus an inverted form of whatever's lying 3 kilohertz above you. So it sounds like you're trying to listen to something and some idiot's working up a sideband over the top of it. That's what it sounds like. Now, there's nothing you can do about that. Blame physics, okay? So the only thing you can do is to change the architecture of your radio so that it is no longer technically a direct conversion receiver. So you could add another mixer and have some phasing going on with your I and Q signals, and you can mathematically cancel out the other sideband. It's called the phasing method. Or you can convert it to a superhet, which basically just means instead of mixing it down to baseband, you mix it down to an intermediate frequency. And then you put your signal through a tiny, narrow crystal filter that's so narrow that it only lets one of those sidebands through. And then when it comes to this stage, when it comes to mixing that down to audio, you ain't got to worry about what's 3 kilohertz above, because there's nothing 3 kilohertz above, because you filtered it out, right? So you can mix it down with confidence and it will sound fine. So anyway, that's why when you're listening, and you'll hear it, because I'm gonna put some footage in of me tuning across the bands with this thing. You're going to hear it. It can sound messy, and for a while it takes a while to get your head around it. If the band's not too busy, it can sound wonderful, because of course there's no filtering, so you're hearing it as much, and it does sound pretty good. But there's no such thing as a free lunch. So anyway, that's how it works. Let's get on with it. Now, at the beginning of last year, I challenged myself to build another direct conversion receiver, but I gave myself 2 important conditions. The first one was I was only going to use analog modules, and the second one was I was only going to use discrete components, right? So individual transistors. So analog modules, so no Arduinos, right? That was hard. Which means there's no little SI5351 phase lock loop signal generator boards, which I put in just about every radio I've built. None of those. And no ICs, right? So it's got to be all discrete components. Right? And that's even harder. One, full disclosure, crept in. Don't blame me, blame Asher Farhan. Because he put a voltage regulator in, and technically a voltage regulator is an integrated circuit. But apart from one voltage regulator which snuck in, it is all discrete components. Now, let me show you, and I'm going to show you the stages. Most of the time is going to be taken with the oscillator, because that's the thing that's most fun, I guess. So the bandpass filter. This is the classic double-tuned circuit, and I use the specifications that Hans Summers of QRP Labs prepared. Poor Hans. I bought a filter from him. And then all the others, countless other ones, I've just built them myself with his excellent instructions. So he's just a bit too good, really, at providing instructions. But they're really excellent. The thing with a bandpass filter is, I've got a video actually on my YouTube channel called The Dark Art of the Bandpass Filter, and it does frighten people a bit, because it's not like a low pass filter or a high pass filter where you do the calculations, you shove the parts in, and it's got a fair to middling chance of working all right. A bandpass filter is way more picky than that, because you've got these 2 separate tuned circuits, and that little you'll see I've got some higher quality variable caps down the bottom. They're part of the respective tuned circuits. That little blue variable capacitor is a little trimmer which controls the coupling between these 2 circuits, and and basically, so you're tweaking all three of these things to get the kind of classic, band pass filter shape and getting it in the right place that you need it. And it is very much trial and error. The transformers on either side, those, essentially the secondary provides the inductance to work against the capacitors, the variable capacitors, but there's another small turning then which provides some impedance matching for the input and the output as well. But the instructions are there, and Hans tells you exactly how to do it. So if you're not sure, in fact, if you've never built one before, I'd say buy one of his kits first of all, follow his instructions, and then have a go at doing one yourself. I think because you've got a better chance of kind of succeeding. I think. But yeah, anyway, so that's the bandpass filter. Now, when it came to the product detector, I played around with a few different ideas. Now, the first one is a design by Pete N6QW of Solder Smoke fame, who, well, it kind of simulates a dual gate MOSFET. It's two JFETs, some J310s, but connected together as though they were a dual gate MOSFET. So, and you'll see he's got some impedance matching down the bottom left there on the RF in, and he's got an audio filter then at the top right, where you can see that 1 millihenry choke, just to filter out any of the RF. You remember I said it produces another signal in the middle of the 20 meter band. Well, that will take that out so that all you're passing on then to your audio amplifier will be an audio signal. So not too difficult to put together. That was it when I built mine, and it worked very well. Now, obviously, it's an active mixer, so you actually get a bit of gain, which is a good thing, because the thing about not having an IF stage is that in a conventional superhet, of course, the IF's where you get all the amplification, really. But the thing with a direct conversion receiver is virtually all of your amplification is coming in the audio stage right at the end. So if you can get a bit of RF amplification, on the way, then that's, no bad thing. So I built this, but I had a bit of a problem. And the problem that I had was AM breakthrough. Now, perhaps if I built this for another band, that wouldn't be such a problem. But of course, just sitting to the north of the UK allocation of the 40 meter band are all these very powerful broadcast shortwave stations like Radio China International. And I can tell you, I was hearing and it has that terrible little jingle thing that keeps, you'll know it if you've heard it. I was hearing Radio China International all the way through the 40 meter band, right down in the CW section, right up to the top here, because it's just so powerful. And this thing can't hack it. It just can't deal with the AM breakthrough, which is a shame because it works. And as I said, your mileage may vary depending on where you live in the world, depending on what band you're building it for. You might well get away with this, but it wasn't really for me. So I kind of had to think again. So I went back to me tried and trusted diode ring mixer, the double balanced mixer. Now forget all this stuff down that I probably can't see you might just be able to see my my cursor here, but forget all this stuff down the bottom with the this is a relay and stuff. It's because I actually ended up putting this in one of my transceivers, so I had the RX and TX switching, which obviously I don't need for the direct conversion receiver. So I built just the standard one. Forget everything really below this point here. It's so the basic mix. I built the basic mixer, put that in. Obviously, I'm not getting as much gain. In fact, this thing will give you a loss, but hey ho, that's how it is. Radio China International was still there. I mean, it wasn't anything like as prevalent, it wasn't breaking through as much, but it was still kind of there a little bit, and it wasn't quite as good as I thought it could be. And it was actually Bill Mara that suggested to me about trying the W7EL, Roy Llewellyn of antenna modelling fame, who many years ago designed this little, well, he calls it an audio diplexer. And this is this bit here, if you can see my cursor, which it's like a kind of audio filter. You've got the 100 microhenry choke here and some capacitors here, but it's also got this 51 ohm resistor here. Now, what this means is that the IF port always sees, pretty much always sees this a good 50 ohm match, and that, as you'll see in a minute, was a real game changer. If you're interested, I'm not going to go through all the details of this now. If you're interested in this, have a look at my YouTube channel. I've got loads of videos about building and testing diode ring mixers, and it is pretty good fun. It's amazing, really, what you can do with some wires coiled around some ferrites and 4 diodes. So anyway, so this is what it looks like. So this was the kind of final one with the you can see it's a trifilar wound transformers. So I've got 3 different coloured wires there to kind of help with that, and you can see the diodes in the ring, the 1N5711s. And here's the little Roy Llewellyn diplexer. Here you can't actually see the choke at the minute, but here's the resistor to ground. Right, I did some testing on this to see how things would compare. So now I should just explain. In order to test how well the product detector is working, I actually kind of, as it were, put it in reverse and tested it as a modulator, because what I could then do, testing as a modulator, you obviously the sidebands and the carrier are much closer physically together, so it's easier to see how effective the thing is working. So this, so what you're seeing is a screen grab from my Spectrum analyzer, and you'll see here. So I tested it at 13.3 megahertz. It's just because I bought a load of 13.3 megahertz crystals, and actually kind of use them to build crystal filters. So I have this kind of weird IF frequency very often. So I know I'm not using it in an IF, but anyway, that's why it's 13.3. So here's the carrier here, and you'll see the carrier, which is number 1, is down at 57.7, and the lower sideband number 2 is at -24. So I mean, it's not bad. I mean, what's that, 10, 20, 30 odd dB, but could do better, basically. Now, I know what some of you are thinking. You're thinking, well, it's your shoddy workmanship, Nick. If you bought a professional one and put it in, it'll work a lot better. You mean like this? Let me show you this again. So that's the one I built myself. You watch that carrier in the middle, right? That's at least 10 dB worse, the so-called professional mixer, than the one I built myself. So it's not about shoddy workmanship, unless we're all shoddy, that is. But let me show you what happens when I did the exact same test, but I included this Roy Llewellyn audio diplexer. So it's exactly the same mixer, same level signals, but this time I've got that little audio diplexer on. You look at that carrier signal now. Can you believe it? Right? From that to that, right? I mean, carrier, what carrier? I mean, it really doesn't get any better than that. I mean, absolutely super. And really, this underscores the importance of this 50 ohm match if you're going to use a diode ring mixer on that IF port. And I'd taken my eyes off the ball on this, because when I'm building it in an IF stage, I'd put an RF diplexer on the port, so it would. But I kind of thought, well, audio, it won't matter with audio. Well, clearly it does. And once I'd got this going, then fortunately Radio China International was gone. And unless I wanted to tune to the proper frequency that it was on, I didn't have to listen to it anymore. So yeah, amazing, isn't it? The difference 50 ohms can make. Right, that's my phone ringing, so just excuse me a minute. Right. Okay, so let's move on to the audio amplifier. Now for this, I decided I was going to try a push-pull amplifier, and this is one that was in Sprat, Sprat 129 by Dieter Genzo W8DIZ. And essentially, it has a complementary paired 2N3904 and 2N3906, so NPN and PNP, in this push-pull configuration. And that's fed by a kind of amp and a preamp here. And that was my version of it. Ignore that transformer in the middle. That was an experiment, so that's not actually in circuit. Now, the good thing about audio circuits, of course, is that you can build them on strip board, which you can't really do with RF, because all those little copper traces act like capacitors, and they send you tuned circuits all over the place. So yeah. So, but and for me, it means I can actually build things a bit smaller, which is always a bit of a godsend. So I should have dusted it first. Apologies for that. All the dust on top of it, sat on a shelf too long. But anyway, so I put it in. It worked really well. But Pete Giuliano contacted me and said, Nick, that's great. He said, but have you tried swapping out that last pair of transistors, the 2N3904 and 2N3906, for some proper audio power transistors? And he said, I did. He said I'd left everything else, all the biasing the same. I just swapped out those and put in the TIP 31C and the TIP 32C. Now, these are proper audio power transistors. And he says you'll get a lot more gain. And indeed, I did. So that was Pete's design. And that's the one I did. And so you can see the audio transistors there and there, and that worked great. So it didn't draw too much extra current, but it certainly gave me more volume, certainly, into the 8-ohm speaker. So that was really good. Now, the oscillator. This is the fun bit, the last bit. And to be honest, it was actually the oscillator that started this whole project off. Because a while ago now, Asher Farhan of Bitex fame, VU2ESE, posted on his website 2 new schematics. One was the S Bitex, his software-defined Bitex radio, really, so very high-tech kind of thing. The other was the complete opposite end of the spectrum, was what he called his Daylight Again transceiver. And this was pretty much all discrete components and all analog, including an analog, well, he called it a PTO, a permeability tuned oscillator. Now, if you've ever had a go at building an analog VFO, variable frequency oscillator, most of them, the Colpitts, Butlers, and all that, tend to have a fixed amount of inductance and then a thundering big variable capacitor, and you tune it by varying the capacitance in the tank circuit. Right, sorry, somebody keeps phoning. Sorry, hang on. You're just gonna have to excuse me for one moment. Susanna, phoning here. Right. Okay. Apologies. So, can't remember where I've got to now. Oh yes, permeability tuned oscillators. So he, So what he did is he 3D printed a little former, plastic former, and he had you could wind your induction loop on the former, and then he had a brass screw that you could turn in and out, which varied the inductance. Now, as somebody pointed out, technically it's not a permeability tuned oscillator because brass has the same permeability, I think, as air. So he's not changing the permeability, but he is changing the inductance, and that's how you could screw it. You could screw it in and out. And I thought, oh, this looks amazing, really. This looks really good. But what really got me interested was when Bill Mara had remembered some conversation he'd had with someone. Somebody had sent him some stuff about some bloke that had done a similar thing, but on a glue stick. So now I'm going to show you some pictures of this stuff in a minute. But if you kind of think a glue stick, it's like a kind of lipstick thing as well. Any of those things, it's a plastic tube, and inside the plastic tube is a kind of threaded shaft, and it has a little kind of plate on it. And as you twist it, the plate goes up and down on the shaft, you see. And so I thought, oh, this sounds amazing. Somebody's built a PTO with one of these things. So I got onto Amazon and bought a whole box of glue sticks, right? So this is the kind of thing I'm talking about. And what you do is you put your windings on like this. And so I did a kind of tap, I think I can't remember how many turns is on there now, but about a quarter of the way through, you tap it. And then on the inside, what I did is, so this kind of grey bit here, this is the little the plate that moves up the shaft, is I glued two toroids, one on top of the other, onto this. So what happens then is when you turn this thing, what you're doing is you're putting these iron dust toroids in and out of your tune. So that's how you're varying the permeability and varying the inductance and how you tune it. And it has the advantage actually over Asher Farhan's design, because Asher Farhan's design, because it's a screw that goes in and out, your whole tuning thing is coming in. Whereas this, of course, just stays the same because all the movement is within the tube, right? So I thought, oh, it sounds amazing. So I had to play around with this. That was the first one I did. The first one I did was pretty random, to be honest. I just picked two random toroids. I didn't know what they were. Glued them in just to see if it worked. Well, it did. But then, as you'll see, I used those yellow T50-6 toroids that I used for that. So here was my little schematic. As I said, this was the first one that I did. So actually, I used some different things. But this is the kind of idea. So I glued one on top of the other inside. And this is the offending voltage regulator that broke my only discrete components rule. And so what happens here then is you've got your basic kind of oscillator, but you're turning and varying the inductance rather than the capacitance. And turns out that is way more stable than the other way around that I've always been used to, which is having fixed inductance and varying the capacitance. And it's not a new thing. If you remember kind of old AM car radios, where you would press the things. I mean, they were all permeability tuned oscillators, but it's kind of fallen out of fashion a bit, really. But it's very interesting having a go at building one on a glue stick. So here's what I actually did in a tin. I built a few different ones. The first one I did was all kind of open plan, but it was like a theremin, really, because as soon as you got near it was woo, because the hand capacitance was changing it, whereas putting it in a tin was shielding it a bit, was a much better kind of idea. So so that's it. Now what else have I got to show you? Oh, only to say, because I did a video about this, and suddenly the viewing figures went through the roof. I mean, suddenly it says thousands of people are watching this video. I thought, why on earth is everybody? And I hadn't realised that Jenny List from Hackaday had picked it up and had run a story on my glue stick oscillator, and so a lot of people were kind of coming to it from there, really. So yeah, it's an interesting little thing. I'm certainly not the only person to do it, and other people have played around with it, and one guy used all kinds of things, lipstick things and all kinds of different things. But there we are. Okay, now I think what I've probably got now is some on-air testing, and just wait to the end, because I couldn't resist doing this little experiment at the end. You're not going to believe this at the end if we're talking about stability of this thing, but I hope you enjoy. Okay, so this was a bit of an experiment, but I just had to try it, really. So I've got almost the same setup as you saw before. So got the PTO connected, drawing about 30 milliamps as usual, except that I've disconnected the speaker here, and you'll see I've got another audio cable connected into that audio output, and that, if I just follow it, ignoring all the graveyard of other projects going on here, going over here, over here, over here, over here, over here, and it comes into finally into this, and this is a little Behringer external audio interface, and that it connects via USB to my Mac, and get a load of this. Yeah, I'm decoding FT8 on a glue stick PTO. Unbelievable. And I'm going to do a screen capture now, so you'll see this in more detail, but I just had to try it, but absolutely amazing. So you can see on my Mac I'm running WSJTX, and I've also got a browser running down the bottom left, and I'm on the PSK Reporter website, and you can see I've got it set up to show all the messages I'm decoding. That's the best one, I think. Asiatic Russia. Yeah, so that's a good old way away, but yeah, plenty of stations across Europe. And you'll see, I mean, look at that waterfall. I mean, of course, there's some drift, and that's evidenced if you look at the right-hand column. You can see that same G0 signal. I'm decoding it, but there's a little bit of drift. I've got it at 1790, then I've got it at 1788, and in a minute you'll see it's 1787. But that's only 3 hertz. I mean, that's quite incredible, really. And, you know, would you use it to decode FT8? No, of course you wouldn't. If you wanted to do FT8, there's far simpler ways to do it. Even if you wanted to take an analog route, you know, you'd use a crystal oscillator or something. But I just do it just to make the point about, you know, how stable this thing actually is, that it will even decode it. Now, I'd let the PTO run for a little while so it was warmed up and it settled down. And it does settle down remarkably well. But you can see from the PSK Reporter map down the bottom there that, you know, I am decoding FT8, and it's really quite remarkable that you can get that level of frequency stability with a variable inductor built on a glue stick. So, and it just kind of makes you realise that, you know, if you can do this, then really SSB shouldn't be too much trouble. But yeah, there it is. Who would have ever thought? You know, glue sticks, is there nothing they can't do? So that is it. Thank you for your attention, and I will take some questions or comments. But if you are interested in finding out about this or any of the other projects and things that I do, then please do check me out on the YouTube channel. You just search for M0NTV and you will find me. But thank you very much, and been good to talk to you.
Okay, well, I certainly enjoyed that. I know why my glue stick didn't